Okay, so we have looked at a bunch of properties of Bessel functions, which are some of these properties we have seen are like the orthogonal polynomials we discussed earlier. Bessel functions are not polynomials. However, there is this sort of analogy one can draw, and there are ways in which we can connect the two kinds of functions. And there is, in this lecture, we will look at one more such feature, namely orthogonality. Right? So there is a sense in which Bessel functions are also orthogonal with respect to each other with respect to wave function, and we will look at some of those details in this lecture. Okay, so in order to work out the orthogonality properties of Bessel functions, we'll start with the differential equation, right, that are satisfied by Bessel functions. Right, we have seen how x squared d squared y by dx squared plus x dy by dx plus x squared minus n squared times y equal to 0 is the differential equation corresponding to which we have the Bessel functions of order n. Jn of x is a solution of the above differential equation. And so it's convenient for the discussion ahead to scale this variable x by a factor of alpha, right? So if we take x and rewrite it as alpha times x, we see that y1 it's going to be a solution. Y1 is equal to Jn of alpha times x is a solution of this differential equation, right? So in place of x I put alpha x, so x squared and there's an alpha squared and alpha squared in numerator and denominator will cancel, and then the second term again I have x and dx in the denominator, so alpha appears in both numerator and denominator, so it doesn't really change anything. It's only when you have x squared minus n squared, that's going to become alpha squared x squared minus n squared. So in place of y I have put y1. Y1 simply means that the argument is alpha times x, and now it's convenient to rewrite these first two terms in this form, right? So you can pull out this factor of x outside, and so we have x d squared y by dx squared plus x plus dy by dx, so that we can rewrite this as d by dx of x times dy 1 by dx, right? So you expand this, you'll see that you'll indeed get back these two terms. So we have, if I differentiate with respect to x, then I'll get just this first term, x squared times d squared y 1 by dx squared. But if I differentiate with respect to x, then I'll just get the second term, right? So it's just a convenient way of rewriting the sum of these two terms. And then this is the term where you get alpha squared x squared minus n squared, and then we have an y1 sitting outside this factor, and that is equal to 0. Now similarly we can argue that if we had scaled this by some other factor beta, right, and if we consider y2 is equal to Jn of beta x, it's going to be a solution of this differential equation, x times d by dx of x times dy2 by dx plus beta squared x squared minus n squared times y2 is equal to 0. Right, so now we will use these two equations 1 and 2, and then try and eliminate some stuff. So it's convenient to multiply equation 1 with y2, equation 2 with y1, and then subtract. Right, so we get y2 times, and then there is an overall factor of x which will come out, and which you can take it to 0. So the reason that's possible is because you have n squared times y1 into y2, and then you have an n squared times y2 into y1. These two will cancel, and then every other term, so this term has an x squared and this term has an x, so you can cancel one x throughout, and so basically you have y2 times d by dx of x times dy 1 by dx. That's the term from here, from equation 1, and then there is a similar term which comes from here, which is the x goes away, then you have a y1 times d by dx of x times dy 2 by dx, right? So these two terms, they go together, and again you have alpha squared minus beta squared times x squared will become x because of the cancellation of this factor of x, times x times y1 y2, right? So there is a y1 y2 here, and there's a y2 y1 here, so we just can write this whole thing as this equal to 0. Now, which in turn can be rewritten as a, the first two terms can be written as a total derivative, right? So you see that this y2, you can actually push this y2 into this under this derivative, because you also can push, if you also push y1 into this, because basically you get an extra term here and an extra term here which cancel each other exactly, right? So if you look at this, for example, you see that the derivative of this product is really can be thought of as dy2 by dx times x times dy1 by dx minus the first term when you take a derivative with respect to y1 is going to become dy1 by dx times x times dy2 by dx. So the extra term that's added, that comes out here will get subtracted with the extra term here. So basically you will get back only this is the only term which will survive here, and this is the only term which will survive here. But it's convenient to write it like this, because clearly you see that we can even think of this as d by dx of this stuff minus this stuff, right, which will prove to be convenient as we integrate next, right? So this term we have left it as it is. So the next step, of course, is to integrate throughout in the limits, between the limits 0 and 1, right? So the first two terms are really a total derivative, so you can simply write it as y2x dy1 by dx minus y1x d by 2 by dx, and with limits going from 0 to 1. You'll see that the limits 0 and 1 are convenient, and you will have certain nice cancellations which happen. And then you have this integral 0 to 1 alpha squared minus beta squared, this whole factor times x times y1 times y2 dx is equal to 0. And now up to this point we have left alpha and beta to be arbitrary, but now we will specialize to the case when these alphas and betas are actually zeros of the Bessel function of order n, right? So you will see in a moment that when you do this, more simplifications are possible, and then they immediately led to the orthogonality condition. So if you choose alpha and beta to be roots of the Bessel function, then what it means is you choose alpha and beta such that jn of alpha is equal to 0 and jn of beta is equal to 0, right? So therefore, here we have to take these limits, right? So you see that this whole stuff definitely has to go to 0 at x equal to 0, because you have this factor of x here and a factor of x here. So the lower limit for sure is 0. It's only the upper limit that we have to try and work out. But here, if you choosing alpha and beta to be roots of the Bessel function, immediately actually gives us also the upper limits individually. Each of these terms go to 0. The reason is you have a y2 of 1 and a y1 of 1 sitting here, but y2 of 1 is nothing but jn of beta x, where x equal to 1, so that is jn of beta, and again y1 of 1 is the same as jn of alpha times x, where x equal to 1, so it's jn of alpha. Both of these, by the choice that we have made, that these alphas and betas are alpha and beta in this case, but we can specialize to alpha and beta can be any of the infinitely many zeros that Bessel function of order n has, and that's it. So therefore immediately we see that both these terms are 0, and so we are left with this equation. If you have chosen alpha and beta to be the roots of the Bessel function, then we have this result, alpha squared minus beta squared times integral from 0 to 1 x times jn of alpha times x times jn of beta times x, the whole thing multiplied by dx. This integral is 0, right? So if alpha is not equal to beta, the only way that can happen is if this factor doesn't take it to 0, then this integral must be 0, right? So that is really the core of the orthogonality condition, right? So if we denote these alpha n going from 1, 2, 3, etc. as the zeros of the Bessel function jn of x, we have the result that the functions jn of alpha n x are orthogonal. We might call it a result. We result that the functions jn of alpha n or x are orthogonal on the interval 0 to 1. So the interval is important with respect to the weight function w of x equal to x. So this is very similar to the kind of integrals we wrote down as orthogonality conditions when we work with orthogonal polynomials, right? So there was a weight function, then there was an interval, and so for Bessel functions too, although they are not polynomials, they are in fact, we define them in terms of a series. So you need an infinite number of coefficients to define a Bessel function, but really they have some properties which make them similar to these orthogonal polynomials. So they have this orthogonality between Bessel functions uh, of the same order. If you take two Bessel functions of the same order and tag them along at in this manner with zeros drawn from two different zeros, two distinct zeros, and then you get this orthogonality condition. Now, if alpha is equal to beta, then of course this integral need not be 0, and in fact it is not 0, right? We can work this out. That's the normalization integral, right? So in order to do this, actually we can go back to equation 3, right? So we want to work out this normalization integral. So you see, if you look at this equation, this is completely general. There is no condition on what alpha or beta should be up to this point. So if you go to this point, this equation, and say that we choose only alpha to be a 0 of the Bessel function, we don't choose beta to be a 0 of the Bessel function, it can be some arbitrary quantity, then we have this condition, right? So alpha squared minus beta, so this part remains as it is. So so this stuff remains as it is, it's only here. So of course when you put x equal to 0, both of these terms individually are 0, and y1 is also going to go to 0 because we have chosen alpha to be 0, but beta is allowed to be arbitrary, right? So that means we get this term. So this term remains. This term remains. Only y1 is 0 at 1. y2 of 1 is not known. We'll just leave it as it is. So and x equal to 1. So we will get y2 of 1 times dy1 by dx. But dy1 by dx is what? We know how to write it. So we have a minus y2 of x equal to 1 times dy1 by dx at x equal to 1. But y2 of x equal to 1 is actually nothing but jn of beta x, right? So y2 is jn of beta x, and if you put x equal to 1, so you get jn of beta here, and then the derivative of y1 with respect to x is nothing but the derivative of jn of alpha x. So that gives you jn prime n of alpha x times alpha, but x equal to 1 is also there. So the numerator is just this, and then of course this factor alpha squared minus beta squared, I can push it to the other side. So I have this condition, for if beta is an arbitrary real number and alpha is a 0 of this Bessel function order n, then we have this result. So now we'll take the limit of beta going to alpha using the L'Hopital rule, right? So then we have to just take the numerator, differentiate it with respect to alpha, with respect to beta, take the denominator, differentiate with respect to beta, and then take the limit beta going to alpha. So we immediately see that this will give us just jn prime of beta, and then we have to put beta equal to alpha. So you get jn prime of alpha the whole squared, and then we have this alpha sitting here. Denominator will give you a minus 2 beta evaluated at alpha, that's minus 2 alpha. So minus cancels with this overall minus sign. Therefore we immediately get this result that this normalization integral is actually nothing but jn prime of alpha the whole square divided by 2. So a compact way of writing this normality condition is like here. So this integral 0 to 1 x times jn of alpha x, x is the weight function, and the interval is from 0 to 1, jn of alpha x times jn of beta x dx is equal to 0 if alpha is not equal to beta, and it is equal to jn prime of alpha the whole square divided by 2 if alpha equal to beta. And it turns out that this jn prime of alpha squared can be written as just jn plus 1 squared of alpha, or equivalently it can also be written as jn minus 1 squared of alpha. Alright, so we'll allow this to be homework for you to explicitly check this. It follows directly from the recurrence relations that we showed for Bessel functions, and so this is a compact way of writing out the whole orthonormality conditions. So let's quickly look at a few plots of this, right? So I mean, what I have done is I have defined this alpha as Bessel. So this is I have taken n, this n here to be 2, right? And I have taken, let's say that I'm considering I have this freedom of it's without loss of generality. I can take any alpha to be any of the zeros. Let me take it to be the 10th zero, right? So this is some syntax for this. So if you want to find out the 10th zero of this Bessel function of order 2, so this is how it is, and then let me compare it with this 5th zero, right? So alpha is this and beta is this, and then I'm going to just plot this function x times Bessel function of order 2 comma alpha x. So this is the argument which shows that whatever is here, alpha x is here, and alpha is defined like here, and then times again a Bessel function of order 2 of beta x, and I'm plotting it between 0 and 1. Let me do this. Hopefully it will get done sooner than later. It's running. It takes a moment for this to run because I guess it has to compute this numerically. Yeah, so there you go. So the idea is that you see that this function is roughly, it's spending almost as much time above as it does below, right? So, and it's going to go to, if you find the area under this curve, it's going to be 0, right? We have already seen that's the orthogonality condition, right? So I could check this explicitly by getting Mathematica to do this integral. So let me see if I have, okay, I have to set this to be phi if I do this, and then it's basically the same code, but now I'm going to do an integration. Let me see what value it will give me. It's going to give me yeah, so because there's a numerical integration involved, it takes some time, but it also might give me a fantastically small number. It's supposed to go to 0. Yeah, you see there are difficulties because of how small this number is. Basically the point is that it's going to go to 0, right? In comparison, so let's see what happens if I choose alpha and beta to be the same. If I take alpha and beta to be both 5, and if I redo the same calculation, you see I get a value which is not 0. And in fact, I could do that here as well. If I do equal to phi, and then if I get it to plot, so this plotting takes some time because I think it has to numerically. There you go. You see that all these values are above 0 and not very large values, and there is this sort of falling tendency, but clearly you can see that if you integrate this curve, it's not going to go to 0. It has to be a positive number, right? You can play with this and check for yourself that not only does it not go to a non-zero value, but we know that the value of this integral is exactly this, right? So if you have access to this, you might play some games and convince yourself that indeed it goes to jn plus 1 squared of alpha divided by 2, right? So then one final comment I want to make is that this orthonormality condition is somewhat like the condition that we are familiar with. So these Bessel functions are also somewhat like sinusoidal functions, right? So sines, what do sines do? They oscillate and then they keep repeating, and Bessel functions also do something like that, except that there is no simple way of figuring out exactly where the zeros will appear. That is one thing, and the other is there is a sort of damping associated with in a Bessel function. The height of each crest is going to be slightly lower than the previous one. It keeps decaying as a function of x, right? In a sinusoidal curve, you don't get any decay, right? It's going to be exactly the same point to which it will return every single time. And you see here from 0 to 1, again you can think of this n times pi as the zeros of this sinusoidal function. M pi is another zero of this function. If n pi and m pi correspond to different zeros, I mean here there is the weight function is just 1, right? So this is a familiar relation, and then we get a half. If you can check this, if you'll get a half if n pi is equal to n pi, otherwise you will get a 0, right? So this is a comment to conclude our discussion of Bessel functions, and then we'll move on to the next topic after this. Thank you.